review some of the basics that you want to know when you're looking at these sorts of problems in general. So these are the methods for testing convergence, okay? And so this is a good thing to either fill in on your own, and I left these columns blank. What you need to know is in the notes. You can fill those in. But this is kind of the hierarchy of how you want to proceed. You want to first try to determine if the series doesn't converge, in the same way that when we evaluate a limit, we substitute in and we hope we're going to get a simple answer. But for a lot of them, of course, they're not going to pass the test for non-convergence. And so then what you do is you use the ones that you know converge. So this is kind of the equivalent of your integral formulas, right? These are the infinite series that you know about their convergence. We've studied them. The telescoping, which aren't that common, but then the geometric and the P series, which are very common and you should definitely know. And of course, what's going to happen a lot of times is they're neither going to pass the do not converge test, but they're also not going to be this nice simple form, in the same way that when you had integrals, they generally weren't one that you could just apply an integral formula directly, right? So then you're going to use these various tests, okay? And so we've talked about everything you need to know at this point to do the homework, to do all the homeworks for this next exam, and to do the exam. The question is, how do we use these rules? How do we apply these tests? And so there's a lot behind this, okay? So 3 helpful hints when you're looking at these is, first of all, to remember these rules about how various classes of functions grow asymptotically, okay? So, it's important to understand that ln of n grows asymptotically less than n to the alpha for any positive exponent, which is less asymptotically than geometric functions. So here our base is a positive number, which is asymptotically less than the factorial, okay, which we recall is 1 times 2 ... on up to n, okay? And there's a couple of reasons why you want to know this. I mean, this is actually important just for general mathematics, but it's very useful when you're applying the test for non-convergence. So let me just show you an example. Before I show you an example, does anyone have any questions about what this statement means, though? Everyone good on this? Okay. So just as a simple example, if you're asked to determine whether or not the following series converges, the series from n equal 2 to infinity of n over natural log of n, with the test for non-convergence, you're going to be evaluating the limit as n goes to infinity of the ANs, right? Well, this is my AN. And in order for, and if this thing is not equal to 0, if this limit's not equal to 0, then we can conclude that it does not converge, right? That's what the test for non-convergence says. And in this case, it's definitely true that it doesn't converge to 0. And the reason you know that is because you know that the natural log n over n alpha converges to 0. So this actually diverges to infinity. Okay, this is one reason why it's useful. The way I use it typically when I'm working these problems is I use it to take a series, a series that's very complicated and that's not obvious how to evaluate, and I replace it with a series that I do know about its convergence. So for example, and let me just kind of show you what I mean here. Suppose you're asked to test the convergence of n natural log n over 2 to the nth. Okay, now technically you can use the tests that we've already used or that we've given, but it's much easier to replace the natural log n by n to some positive power. So the smart move here is to replace by n to the alpha, and I can choose anyone. I'm just going to choose just n to the first. Okay. So if I do that, the series I'm looking at now is n equal 1 to infinity n squared over 2 to the nth. Now the reason why I do this is because I know that natural log n is less than n. So now I can actually use the comparison test. Okay. And so if this thing converges, the comparison test tells me if this converges also. And it turns out that it does. So now what I'm going to do is I'm going to use another test to evaluate this, and we're going to see which tests are useful. Okay, so I could use the ratio test. And what the ratio test is going to tell me is that this converges. And so now the comparison test tells me that because this infinite series is greater than this infinite series, if this one converges, that has to converge. And so this is a more subtle variation of what we're doing, but it's very, very useful. It'll save you a lot of time. Okay? Two other quick hints that will help. If you're dealing with a series that has negative terms, and this happens a lot, ignore the negative sign. So in other words, a lot of these series have this sort of form. Where the u to the n's are non-negative, okay? And what you're going to do is you're going to replace this by the series where the terms are all positive. And you're going to test the convergence of this series. And if this converges, this has to converge. Okay, so if this converges, our original series converges. I did not get into this topic. It's in the text. You're free to read it. But this is a notion known as absolute convergence. Okay, so this if a series converges absolutely, meaning that the infinite series of the absolute value of the terms in the series we're adding up. If this series converges, then you're guaranteed that your original series converges. Okay, and the last is, if you have a series that has terms that you can split up. So if I had an infinite series where I was looking at the sum of a series that itself could be represented as a sum, what I would do is I would break these two terms up. And I would look at these infinite series separately. And if each of these converges, it's guaranteed that this converges. So if they both converge, then our original series converges. Okay? So these are things that whenever and here's how I look at it, we've talked about this before, when do you use these rules? And the answer is when you're stuck. When you're working a problem and you're trying these tests and it's not working, then chances are there's a little, I'm not going to call these tricks, but there's a little bit of manipulation you have to do. And these are the 3 tools that are going to help you to manipulate things. Okay? All right, questions on anything before we begin? Everyone's good? Okay. I'm going to try to, give me 1 second here. Okay. All right. So I'm going to go ahead. I'm just going to work through the first couple of problems, kind of outline it. We'll just talk through it and kind of see what we should do, okay? Kind of get an idea of how to approach these. So the first problem in the handout, so these are the handout problems, and these are the problems on the last handout that I posted, right? So problem A it wanted us to determine if the following infinite series was convergent or divergent. So it was the sum from n equal to 0 to infinity, 2 to the nth plus 5 over 3 to the nth. Okay? So what thoughts do we have about this?
You could split it up.
Let's try it. Can't hurt, right? I mean, here's the thing. It never hurts to split it up. You've taken a complicated problem and you've made it into two simpler problems. So there's no way you can lose, right? So let's go ahead and try to split up the series. And so in the same way that I called integrals S, I'm going to call this S, okay? So what I'm going to do is I'm going to look at the two series, and I'll call the first one S1. Okay, and the other one is S2. So this is what we mean by splitting them up, right? Okay. And what is my goal? Well, I want to see if these two converge, right? This is my goal. If each of these converge, then my original series converges, right? Can I say anything about the convergence of either of these series?
Looks like you could do like a root test on S1.
Okay, I could do a root test. So I could do a root test on S1, okay? So what does the root test say? Well, the root test says that I'm going to look at the limit as n goes to infinity of the nth power of my terms in my terms in my series, right? So I'm just going to plop this in here. And this is going to be what they call rho. And of course, rho might not be a number. It turns out rho might be infinity, right? It might be what we call extended reals. It might not even be a real number. It might blow up. Okay, and in this case, when I do that, what's going to happen? Well, a couple things to remember. There's a couple of exponent rules that we want to kind of recall here, right? A to the nth over b to the nth, it can be written as a over b to the nth, right? And another useful rule is that the square root of two things, I'll call them x over y, the nth root, can be written as the nth root of the numerator divided by the nth root of the denominator. Okay. And so using either of these facts, what am I going to get when I evaluate this thing inside the limit? So if we just look at
2/3.
Exactly. So
2/3.
Nth root of, and the easiest way is to rewrite this like this, and of course the nth root and the nth power cancel out, and I get 2/3. And so now I'm going to find out that the limit as n goes to infinity of the nth root of 2 to the n over 3 to the n equals 2/3. And what does the root test tell me about this rho? This is my rho, right? What does the root test say?
That if rho is less than 1, then it converges.
Exactly. So this thing is less than 1. Therefore, and I'll use our lazy little mathematicians, therefore, S1 converges. Okay. All right, good. Now there's an easier way, actually. And this is perfectly fine. This didn't take too long, and if you know these rules, it's pretty straightforward. What's another way I could have done this problem? Okay, so go back through the hierarchy, right? If I use the test for...
We have done We've done like 2n plus 5. Like sort of you do 2n plus 5 plus 1 over 3. The way you could split it up.
Right, and so we have done that part, right? So we have split it apart, but when we're looking at the individual series, and I'm still on S1 here, what is a faster way to do this, though? So one of the things you want to ask yourself is, does this look like a series whose convergence I know about? So notice that when you use the test for non-convergence, you're going to pass, right? Because it's the limit of 2/3 to the nth power. Does this series look like any of these, though?
Yeah, it looks like a geometric.
It is. Okay, so in this case, I can also use the fact that this is a geometric series. And the reason why is I can use this factor right here, okay, and I can rewrite this like this. Now this is a geometric series. Okay. And I know, so here's one thing to remember. Those formulas for the known series that converge, they're like the integral formulas. They're taken for granted. We've already proven, we already know this. So I know, because this is a geometric series, that this converges if whatever this base is less than 1, and it is. Okay? And so we're done. And the nice thing about knowing this is we not only know that it converges, we actually know what it converges to. Notice with the root and ratio test, we don't know. I actually know what this converges to. I know that S1 is 1 over 1 minus 2/3, or 3. You got to be careful you're starting at 0, right? But if you're starting at 0, you actually know what it converges to. So this is a little faster, okay? Now, bearing all that in mind, can we apply this sort of thinking to this guy here?
Yeah, S2 looks like another geometric.
It is. So one of the things you should always remember is that, we made this analogy with infinite series and integrals, right? We said an infinite series is like an integral. Well, it's like it in a lot of different ways. Notice that, first of all, the summation distributes. Okay, so remember before you had this rule that when the integral of the individual functions exist, the integral of the sum is the sum of the integrals. Okay? Same thing here. But remember that we also had this rule that when you had a number multiplying a function, the number came outside, right? Well, the same thing is true here. Okay, so I can factor out numbers. Now I have n equals 0 to infinity, and I'm going to write this in a kind of sneaky way, 1/3 to the nth power. Okay? So I factored out that 5, and I wrote 1 over 3 to the nth as 1/3 to the nth power, because of course 1 to the nth is 1. And sure enough, I know again, this is another geometric series. And I know it converges because the base here is less than 1. So it converges because the base, whoops, I'm still on the other problem there. The base is less than 1. Okay? So we can put it all together now. So how do we kind of put this together? We say, okay, since n equal to infinity of 2 to the nth over 3 to the nth, and the summation n equals 0 to infinity of 5 over 3n both converge, then the infinite series of the sum of these two terms converge. Okay? And that's how we write that up. So one of the key things you're doing when you're writing up your problems is make sure any sort of result you use, okay? Like here, notice I'm saying why I'm saying this converges, okay? I'm saying it's a geometric series. here I would say I'm using the root test, right? And then I would write out the thing I have to evaluate for the root test, okay? So make sure that whatever sort of reason you use or whatever sort of test you use, you're going to explicitly state that, okay? All right. Everybody good on that? Okay? Okay. Let's look at the next problem. So problem B asks us to determine whether or not this infinite series converges. Okay. So one thing to always do, test, you want to test for non-convergence, right? So in this case, the limit as n goes to infinity of 7 over 2n plus 5 to the nth. What will that be?
Zero.
Okay. And how do you know that? What is kind of your logic?
Oh, because it'd be 7 over, and then when you plug in the infinities for n, that whole denominator just becomes infinity. And so, any number over infinity is 0.
Right. So one way of looking at it is to kind of think of this as this is infinity to infinity. So that's going to be infinity, and anything over infinity is 0. You might also notice that we know that for any fixed number, I'm erasing for some reason. Hold on. For any fixed number, we know that a to the nth, if a is greater than 0, this thing converges to positive infinity. And so these terms become greater than any fixed number. Okay, so if you start at n equal to 0, this is 1. N equal to 1, this is already greater than 5. Okay, so this thing is bounded above from by this. Okay, and that converges to 0. This has to converge. So this is kind of like a squeeze theorem sort of argument. Okay, all right, good. Test for non-convergence works. Does this look like any of our known series? Let's go back up and look at the series that we know about how they converge. We have telescoping. Okay.
Is this a P series?
So here's a good question. Is it a P series? That would be the first thing that you would think. It's the only thing it could possibly be. Is it a P series? Why or why not? Okay, the answer is it isn't. And the reason why is when you're looking at a P series, it looks like this, 1 over n to the P. The P is a fixed number. Okay, so with the P series, the P is some fixed number. Why? Let me move this down. For some reason it's hard to write in that part of the screen. So when we're doing a P series, this P is a fixed number, right? Notice that the P is not, the exponent here is not a fixed number. So unfortunately, we can't use any of our nice results. So now we have to use an actual test, okay? So, can't use any of our formulas. And the question is, now we have to use one of our tests. And the question is, which one? This is not an easy question, by the way. Anyone want to take a shot?
Do we do the integral test?
So this is an excellent question. Do we do the integral test? Okay, so first of all, you might think integral test, because to do integral test, I always have to have positive terms I'm summing up, and I have that, right? However, to use the integral test, when I replace n by x, I have to be able to do the integral. So the question is, do you know how to integrate this function? Whoops. So 2x plus 5 raised to the x power. Do you know how to integrate that? I don't know how to integrate that off the top of my head, okay? So, because we don't deal with these sorts of functions, right? These are, again, to kind of go back to Anil's question, which was a really good one. Notice that this is not an exponential, nor is it a power function, okay? So integrals out, unfortunately, right? So what I do is I replace n by x, and I see if I can integrate this. Now, so here's the thing. I look at this. I have root, ratio, and comparison test, right? Again, I'm looking at the form of this, all right? So here's what I want to come back to. Excuse me. So I have root, ratio, and comparison test. I'm looking at the form of this. What does it look like I could use?
You could try root test.
I could try the root test. Now, there's one little thing you have to know to use the root test to really understand what you're doing. This is not so obvious. This is another little fact. I probably should put this with my other 3 facts. If you have a positive number the limit as n goes to infinity of the nth root of a is equal to 1. That's a nice little fact. Okay. So what it says is, that if a is greater than 1, the nth root keeps on reducing, keeps chopping down the value to 1. If a is positive but less than 1, the nth root actually keeps increasing it up to 1. Okay? So I'm going to use that fact. I'm going to use the root test, okay? So here my an is 7 over 2n plus 5 raised to the nth power. And the root test tells me to evaluate the limit as n goes to infinity of the nth root of, and technically you should use the absolute value, but we don't have to because all our terms are positive. All right. And again, if rho is less than 1, converges. If it's equal to 1, the test is indeterminate. Can't tell. And of course, if it's greater than 1, it diverges. Okay. Okay, so I'm going to do that now. So let's see how this works. So I'm going to take the limit as n goes to infinity of the nth root of 7 over 2n plus 5 to the n. Okay? And remember what we just said a second ago, right? Is that the root of the ratio is the ratio of the roots, right? See, all these little limit rules that we learned before, and you were going like, oh, why are we doing this? Well, this was the reason why. Okay. And now I'm going to simplify this, right? I cold-bloodedly set this up so that the bottom, the roots, the powers would cancel, and I get 2n plus 5. And remember our other limit rule, right? If we have a limit of a ratio, and the limit of each of the numerator and denominator exists, I can just replace it by the limits of the numerator and denominator. So let me just say this very quickly. So the limit as n goes to infinity of f sub n over g sub n is equal to the limit as n goes to infinity of f of n, limit as n goes to infinity g of n, provided that both limits exist and the bottom limit's not 0, right? Okay. So I can do that here. I can use the fact that the nth, the nth of the limit of the nth root of 7 converges to 1. Okay.
are we gonna have to use L'Hopital's then?
Okay, technically you could use L'Hopital's, but I'm trying to avoid that, okay? Here's how I look at it. I think of L'Hopital like any other rule. When you really get lost in the woods and you're really totally unclear what to do, you could use L'Hopital's. And you're absolutely right. If I wanted to, I could take the natural log of this and I could use L'Hopital's and try to evaluate it. But I'm not going to do that. But you could.
Well, no, because if you do, isn't it going to be 0 over infinity if you take the limits?
This is going to be 1. Okay.
Oh,
Because remember this limit here. This is a really important fact. And this is a fact that I don't know that they emphasize this a great deal in high school. Okay. If you take the nth root of any positive number as n goes to infinity, it converges to 1.
okay.
So this
Oh, and is that because is that because then that would be 7 to the 1 over n, and that would be 1 over infinity, which would be 0, and any number to the 0 is 1.
say that again?
Is that because like the nth root of 7 would be 7 raised to the 1 over n, right? And then n being infinity, that'd be 1 over infinity, which would basically be 0. So then it'd be 7 to the 0, which is just 1.
You could actually think of it that way. That's actually a really nice way of thinking about that. So if you wanted to kind of think about that way, you could think of it as that, right? As this is going to infinity, that goes to 0, and that converges to 1. Yeah, that's actually a nice way of looking at it. So now we're going to get 1 over infinity, and that's going to be, this is our row. Okay, it's 0, which is less than 1. So it's going to converge, okay? Now, let me show you a simpler way using the comparison test. This is perfectly fine, okay? There's no problem with that. What I'm going to do is I'm going to look at something that I know that converges, but that is greater than this. So I'm going to use the comparison test. And I'll show you how much faster it is and why we use it. I'll put this in a different color. So what I'm going to do is, I have a feeling that this is going to converge. I mean, common sense tells you that the top number is fixed, the bottom number is getting larger, it's getting very small, and it's probably getting small at such a rate that it is going to converge, okay? But here's kind of a nice way of showing that rigorously without having to use too much intuition, because intuition can lead you wrong if it's not backed up by some mathematics. So I'm going to start off using this fact right here. That this guy is less than this. Okay, everybody agrees, right? For all n equal to 1, 2, 3, ... And I should use less than or equal to, right? Okay, everybody agrees? Okay. And then,
how would it be less than?
because notice that this number on the bottom, so notice here, so that's an excellent question. How do you know that? It takes a little while to kind of see this. So notice that 2n plus 5 is always greater than 5. Well, again, greater than or equal to, right?
Yeah.
Okay, therefore 2n plus 5 to the nth power is greater than or equal to 5 to the nth.
Yeah.
So when I flip them, the inequality flips. So basically, it boils down to the fact that the denominator here is always at least as big as this one. N equal to 0, it's equal to, but when n's not equal to 0, this denominator is always bigger than this denominator.
Oh, I see. Okay.
And the reason why I did that was because if I ignore the n term, I know how this behaves. So this is like my an, and these are like my bn's. And so I know that this infinite series converges because it's a geometric series. Because it's a geometric series. So if the series where the sequence where the terms in the sequence I'm adding up to converge, and the terms of this sequence are greater than the terms of this sequence, this tells me by the comparison test that this has to converge. Okay? So this is by the comparison test. This has to converge. I'm going to let you soak that in for a minute. Okay, questions we have?
For these, could we technically have taken out the 7 like as a constant before we even began, or is that a thing you can do?
Exactly. And if I was doing, and I was going to say this, but I don't want to go into too much detail. But if I was doing this myself, I would ignore it. Who cares? I mean, if the thing goes to infinity, multiplying it by 7 won't make a difference. If it doesn't go to infinity, multiplying it by 7 won't make any difference. So you're absolutely right. I'm really interested in this, and that's a good observation, because it helps me actually focus on what I'm actually interested in, what the real point of this question is. Okay. So here's the whole point of the comparison test: is I replace something ugly and complicated by something simple that I know its convergence. Okay. And of course, notice this: the reason why this works is because the series that I know that converges is less than the one that I don't know about. That's why the comparison test works. Okay. Okay. So there's more than one way to cat a skin, as we say, right? All right. Okay. On to C. CC. You guys have not dealt with factorials a lot. Some of you have. But factorials arise a great deal in probability theory. So we want to figure out what the convergence of this is, okay? Now, one hard and fast rule, there aren't a lot of hard and fast rules, but there's one hard and fast rule, is that when you have factorials in a series, we almost always use the ratio test. That is your go-to test. This is your go-to test when you see a factorial. And the factorial, of course, is this exclamation mark. It doesn't mean that it's excited, right? This is a set of instructions telling you to multiply numbers. So, and the reason why is very, very simple. It's because you do not know how to integrate factorials. They're actually incredibly hard to integrate. Okay, so the integral test is not going to work, and the root test is not going to work, because figuring out what the nth root of n factorial is not easy either. There is an answer, but it's going to take a lot of math to get there. So nothing that we know is going to help us when we have factorials. Okay, there's no nice simple results. Okay, what I want you to do, so I'm going to use the ratio test. What I want you to do is I want you to set up the ratio test. Let's spend a few minutes and set that up and see what we get. Okay. So let's set up the ratio test. And I want to see what you get. So we'll take about 2 minutes. Is that okay? A couple of minutes. If you have any questions, feel free to ask, because you will not be the only one.
For factorials, is it possible to take out a constant as well? Like, could you take out the 2?
No, and that's an excellent question. Very good question. And the answer is no. And let me show you why, because this kind of goes to the question that a lot of other people have, but they haven't quite got there yet. 2n factorial. So when you have anything in here factorial, this is instructions telling you multiply 1 times 2 times 3. all the way up to whatever's in this argument. So this is a set of instructions telling you multiply 1 times 2 times 3 times 2n minus 1 times 2n. Okay, and that's why that 2 cannot come out, because this is part of the quantity that I'm taking the factorial of. It's an excellent question. Okay, if you guys don't mind, I'm going to go to the restroom for just 1 minute. I'll have you guys work on this. I'll be back not even in a minute, okay? Okay, I'm back. Sorry about that. Okay, so do we have an answer? Do we have questions? Do we have anything? Okay, so first of all, what does the ratio test tell us to do? Anybody? Hello?
To replace n by n plus 1 and then have that whole thing over the original with the regular n or whatever.
Right. So the reason why it's called a ratio is because what we're doing is we're taking the limit as n goes to infinity of successive terms in the series we're adding up. Okay? And we're looking at this. And one of the cool things about the ratio and root test I always loved as a student is the fact that you make the decision the same way. Even though you're evaluating different things, okay? It's the same rule, right? If this is less than 1, converges. If it's equal to 1, it's indeterminate, right? And if it's greater than 1, it diverges, okay? So that's kind of nice. Let me just give you a piece of advice, okay? The piece of advice is evaluate these expressions off to the side and then flip the an. And I know you may think I'm being kind of pedantic here, but trust me, it's easy to make dumb mistakes. So I'm going to write out an plus 1. I want to write out the expression for it, right? The expression for an, and then I'm going to flip it and multiply it by an plus 1. Okay, so first of all, an is easy, right? An's just your original, you just pick it off, right? This is a sub n. Okay? Easy peasy. So for one of them, there's no work. What about an plus 1? Well, I think it was Derek who said what? Said replace n by n plus 1, right? So that's what I'm going to do. This is going to be 2 times, and now in place of n, I'm going to put n plus 1, right? Everybody with me here? Times, these are factorial.
When you put all that over the original function?
Right. Now I'm going to make this ratio. What I'm going to do is I'm going to flip the an and multiply it by an plus 1. Okay? And let me do it like this. So now I'm going to say the limit as n goes to infinity. I'm going to flip this guy. So when this guy becomes flipped, 1 over an will be n factorial times n factorial over 2n factorial. Okay? Trust me, this is a good thing to do. You would be surprised at how easy it is to screw up the ratio for the expression if you don't do this, okay? All right, so when we get this all done, this is going to be 2n plus 2 factorial. I'm going to have an n factorial and an n factorial here, right? On the bottom, I'm going to have a 2n factorial. And then I'm going to have an n plus 1 factorial times an n plus 1 factorial. Okay? Everybody good? Now, what do you think is going to happen next? What do you foresee occurring? I have no freaking clue what that is, just by looking at it, right? It's a god-awful mess.
Combine like terms, maybe?
That's a good suggestion, but here's kind of what I'm going to do. So let me just kind of show you the simple way of doing this. I'm going to notice that n plus 1 factorial and n factorial, they're going to cancel out to some degree, okay? And let me just show you with a simple example, okay? Suppose you have 6 factorial over 7 factorial. Let's look at actual numbers, right? So 6 factorial says this is 1 times 2 times 3 times 4 times 5 times 6. 7 factorial is what? 1 times 2 times 3 times 4 times 5 times 6 times 7. Because notice when I'm doing 7 factorial, I'm multiplying up to 6 and then a little bit further. So that's 1 over 7, right? So I'm going to use the same thing. I'm going to notice that I can simplify each of these guys. What I'm going to notice is that n factorial over n plus 1 factorial, what will it give me? Here I'm multiplying everything up to n, right?
This one at the bottom?
Close, close. N plus 1 factorial, I'm multiplying from 1 up to n plus 1, right? Okay.
1 over n plus 1?
Bingo. Nice, huh? And that's why the ratio test works with factorials, because factorials will cancel out like this, okay? So, 2 of the guys I know. Now the question is, what about this first guy? So this guy I know is 1 over n plus 1. This guy I know is 1 over n plus 1. The question is, how am I going to handle the first one? So now I want to do 2n plus 2 factorial over 2n factorial. So here's the thing to recognize, is that this factorial contains this factorial inside of it, right? Here I'm multiplying from 1 up to 2n plus 2. Here I'm multiplying by 1 up to 2n, right? So this looks like, 1, 2, ... and I'm multiplying it out to 2n, right? This looks like I'm multiplying from 1, 2, ... 2n times 2n plus 1 times 2n plus 2, right? And of course, what happens? Everything cancels, right? Everything cancels except this guy right here. Alrighty?
So you get a quadratic.
I'm going to get a quadratic in n, and so what I'm going to do first, because you're right, it's going to get complicated. That's the key observation. It's certainly going to get complicated. I'm going to put these simplifications back in. So I'm looking at the limit as n goes to infinity. Well, I'm going to have a ratio still. The first term in that product gave me 2n plus 1 times 2n plus 2. That was our first guy right here. This guy is going to be 1 over n plus 1. The second factor is going to be 1 over n plus 1. Now the question is, what does this converge to?
Professor, you wrote 2m plus 1 on top 2 times.
I was just testing to see if you were paying attention. Thank you. Okay, so everybody's good, okay? Let me ask you a question. Would it help a little bit if I posted like a little tutorial on factorials? See if I can find a little Khan Academy video or something like that?
Very much.
Yeah,
Okay.
Maybe so, yeah. It's not really explained well upon in high school.
Okay,
Yeah.
that's perfectly fine. Okay, so now I'm at a point where I can evaluate this. So notice I have a limit at infinity, right? When you have a ratio and a limit at infinity, going back to Calc 1, what do I do? Begins with an L. Leading terms?
Right.
Sound familiar?
Yeah.
Because you want to see what goes on asymptotically, right? So only the biggest terms. So this is equal to the limit as n goes to infinity. Leading term in this quantity is 2n. Leading term in that quantity is 2n. Leading term in this quantity is n. Leading term in this quantity is n. And you get 4. Okay? We go through all that work and we find that rho is equal to 4. Right? So what do we decide? Diverges. Okay. If you try this using any other method, unless you know a great deal of advanced mathematics, you will not be able to do this when there's a factorial. Factorials just scream out ratio test. If it's not a direct ratio test, it's a ratio test combined with a comparison test. But the ratio test is going to be in there, I guarantee you. So that's nice. Okay. Questions that we have on that? Okay. Well, let's go on to our fourth problem then. Okay. So our fourth problem in the handout. So this is D. So we want to look at whether or not the following series converges. Okay. That's sine, by the way. Okay. Does this converge? Okay. I look at this. First of all, I want to test for non-convergence, right? So if I test for non-convergence, and this actually becomes important when you have trig functions, because trig functions are insidious in the sense that a trig function the infinite series might not converge and it might not diverge. It might just oscillate. Okay. So when you have trig functions, you want to kind of pay attention, be a little careful. So when I use the limit as n goes to infinity, whoops. This is going to converge to 0 for sure. Okay. How do I know that? Well, as n goes to infinity, this goes to 0. Sine of 0 is going to 0. 0 raised to infinity. And technically, you're absolutely right. I should use L'Hopital's. I know someone's going to say it, but this does converge to 0. Okay. So if you want to test that, you can use L'Hopital's rule, but this is going to converge to 0. All right. So here's kind of a little hack. All right. Most people, unfortunately, when they do these problems, they don't test for non-convergence. So this is a test for non-convergence. And I'll be honest, this test is not totally easy to do. Okay, because, you know, you're looking at n natural log of sine 1 over the square root of n. Okay, which you're going to have to write as natural log of sine 1 over the square root of n, 1 over the square root of n. Okay, this is, I'm sorry, 1 over n, sorry. So technically, if you wanted to do this, okay, it's not so easy to do it. Most people skip this step. Here's how I look at it in practical terms. You should do this, but if it's too complicated, skip it. If when you try the convergence test, you can't get anything else to work, come back and say, hey, maybe it doesn't converge. Then put the work into doing the convergence test, okay? I think of the test for non-convergence as like low-hanging fruit. When you can apply it and you can rule out convergence, do it. When it's really complicated, like technically to do this is actually a little involved, okay? I'm probably going to skip it. Okay, and I'm gonna try to see if it converges with another test. If I get another test to work, fine. If I'm spinning my wheels and none of the other tests work, I'm gonna say, you know what? Maybe it didn't converge in the first place. Then I'm gonna go back and try to test for non-convergence. Okay, so you know the non-convergence test is kind of like brushing your teeth. You should do it after every meal, but sometimes it's not convenient, right? So you don't do it. Okay. So does this look like any of the series I know? No, it doesn't, right? It doesn't look like a telescoping series. It doesn't look like a geometric series. The geometric series would be a number raised to a variable power. And it doesn't look like a p series because it's not 1 over the variable raised to a fixed number. So it's none of those, right? So we're going to have to use a test. What test are we going to use and why? And I want to hear from somebody new. So let's see who's online. Hold on. So Luke, what test would I try here? Do you think?
What test would you try?
I have to try a test. None of my easy things work.
I'm not too sure.
So you want to look at the form of this. So you want to look at the form. So if I have a factorial, I know I'm going to use the ratio. When I have a power, where the power is the index, right? I have something raised to the nth power. What am I going to use? The root test. Okay, so let's go ahead and try that, okay? That's what makes sense. Okay, so the root test, I'm going to do the limit as n goes to infinity, and I'm going to take the nth root of sine raised to the nth power 1 over the square root of n. And I'm going to notice, of course, that the nth root and the nth power are going to cancel, right? So this is equal to the limit as n goes to infinity sine of 1 over the square root of n. Okay? And this limit's going to be what? As n goes to infinity, what's going to happen to the argument here? this whole thing. Anybody? As n goes to infinity, what happens to square root of n? Goes to infinity, right? So 1 over the square root of n is going to go to what?
0.
So sine of 0 is?
0.
0.
Yeah. That's where knowing your trig functions is important, right? Sine and cosine and 0. So sine of 0 is 0. So now I know the answer to my question, right? So I found out that this is less than 1. So 0 is less than 1. And this implies that my series converges. If I wanted to, I could put by the root test here. Okay? A really good thing to do is to look at this table and kind of fashion it in a way that makes sense to you, way up here, okay? So, root test works well when I have exponential functions, okay? So an exponential function is when you have a number raised to the nth power, right? All right. And it doesn't have to be exponential. Like we said before, in that problem that we had a second ago, we had 2n plus 5 raised to an nth power, okay? So it doesn't even necessarily have to be exponential, but it works well with exponential functions. Okay, so we know that does converge. And that's really the only way to do that problem. I don't think that there's any other way of doing that problem. That's probably the only way. You could use the comparison test actually, because sine to the nth is always less than sine. If you wanted to, you could use the comparison test too, but you don't really gain anything that much by it. Okay. All right, let's sally forth. Look at our next problem. We want to look at the convergence of the infinite series from n equal 1 to infinity of 4n times n factorial squared over 2n factorial. Okay. Now, this is a test. This is kind of goes back to my statement in the last problem. Testing for non-convergence is going to be really hard. Okay, it's not so easy. So this is a situation where we're going to skip the non-convergence test because it's not easy. All right, and moreover, this form of this infinite series doesn't correspond to anything that we have a formula for. As soon as you see the factorial in there, all of the known series that we have go out the window. Okay, so the factorial precludes our ability to use any of these known converging series directly. Okay, so we have to use a test. What test do we use and why? I have factorials, right? So when I have factorials, what is my go-to test?
Ratio test.
Always. Even on a Sunday. Okay. So I'm going to set these guys up. I'm going to use the ratio test. an plus 1. What is the expression for an plus 1 going to be? Who wants to help me out here? Luke, I'm going to pick on you again. What should I write for my expression for an plus 1? This is an, right?
Yeah, so it'll just be like 4 to the n plus 1 times n plus 1. N plus 1 factorial squared.
Good.
The whole thing squared, yeah. And then over 2 times n plus 1 factorial.
Excellent. Notice I'm being very, very liberal with parentheses here. Okay. All right, good. And what some people do is they write this, they write an on the bottom, okay? And of course the an is just what you're summing up. There's nothing to write really, okay? And then I'm going to flip this and I'm interested in the ratio, right? So the ratio of an plus 1 over an is equal to, and this will be 4 to the n plus 1 over n plus 1 factorial times 2 to the n factorial, okay, over 4n times n factorial squared. Oh, I'm sorry, this guy was squared. Sorry. That's why I put that bracket and I didn't follow through. Okay? Over 2n plus 2 factorial. And the hallmark of a problem when the ratio test is suited for that particular problem is that you'll get a lot of cancellation. So the hallmark of a good ratio problem is that you'll get a lot of cancellation. And what I'm going to do to kind of highlight that is I'm going to break this apart. I'm going to break this apart like this. Okay. So I'm breaking it apart as 3 factors, okay? Everybody good at this stage?
Yeah.
Okay. And now I'm going to do my cancellation, right? So here I just have a 4 left on top. Okay, I'm going to put a bar here. Here I just have n plus 1, right? N plus 1 factorial over n factorial is n plus 1. So something to convince yourself of. Okay, and that's being squared. So I get n plus 1 squared. Okay. And on the bottom, we did this problem a second ago, right? Here I'm multiplying from 1 to 2n plus 2. Well, that includes the product from 1 to 2n, right? And what I have left over is 2n plus 1 over 2n plus 2. Everybody good? Okay. Now notice something unfortunate that's going to happen. I have to evaluate the limit of this ratio, right? The limit as n goes to infinity of 4 n plus 1 squared so a limit at infinity, I'm going to use leading terms, right? So this is a limit as n goes to infinity to 4. The leading term here is n, right? In this quantity right here. I'm going to get n squared. The leading term here is 2n. So I'm going to get 4n squared. Okay. And of course, this is equal to 1. So what do I know? Well, what does the ratio test tell me? It tells me that when I look at this ratio, right? And I get 1, what can I conclude? Not a darn thing. Test is inconclusive. So we don't know. And moreover, there's no other test you can use to make that determination. So on an exam, you would just have to leave it like this. Okay? If I had another test I could run, I would try to run it. It might work with another test. But in this case, there's no other test that I can run, okay? And generally, when one test is inconclusive, other tests are inconclusive. And the reason why I won't get into a long thing about this, but the reason why is the mathematics they're based on is all the same. They're all based on a geometric series sort of argument. So when one doesn't work, the other ones tend not to work. So this is one where we actually don't get an answer. In real life, if we wanted to determine this, we might try to do this computationally. However, it turns out that this is really hard to compute because this increase is too big even for the computer to do. If you were to try to say, okay, let's look at the partial sums, right? We'll use the computer. The response to that is good luck with that, because factorials increase so quickly that you won't even be able to evaluate this expression. So how do people do this in real life? Well, I'll show you this for fun, okay? There is a result known as Stirling's theorem. And Stirling's theorem tells us what happens as n gets really large in a factorial. So here's what, I'll just show you this very, very quickly, okay? Stirling's theorem says the following. Stirling's theorem says that as n gets very large, this is approximately equal to 2 pi times the square root of n times n divided by e raised to the nth power. Okay, and that's an approximation. So if you wanted to actually figure this out a little better, you would use this approximation. Okay, but anyhow, that we don't have to use that. This is just called Stirling's approximation or Stirling's theorem. It's amazing. Stirling lived like back in the time of Newton, and to get this approximation is just like mind-blowing how he did it, because it's actually not easy at all. It's really cool. Okay, so that one we can't get an answer to. All right, any questions on this? All right. Okay, so let's move on to our next problem. So we're 1, 2, 3, 4, 5, 6 problems in. Okay. Problem F. This is from n equal to 3 to infinity, 2 to the nth over n squared. Okay, what should we use? Now, this is tricky. We're going to try non-convergence first. I'm sorry, it's n squared. My bad, I'm sorry. 2 to the nth over n squared. Okay. Here I'm going to use the test for non-convergence because I have two functions and I know how they behave relative to each other as n gets really large, okay? So I'm going to try the test for non-convergence. So I'm going to look at the limit as n goes to infinity of 2 to the n over n squared. Does that converge or does it diverge? Do I know?
Diverge.
It diverges because we know that power functions are asymptotically less than exponentials. This is an exponential function. In fact, this is the exponential function right now that's going on with the COVID infection. Okay, it's 2 to the nth power. So this is a exponential function. We know that the power over the exponential as n goes to infinity goes to 0. So this goes to infinity. So we already know it doesn't converge. It's not equal to 0. So we already know it does not converge. Okay. Now suppose you weren't going to do that, or suppose you skipped the test for non-convergence. What would be the test that you would try, do you think? This is a little tricky. What test do you think you would try?
Ratio.
That's actually the right answer, and that is not so obvious because it's very tempting to say root because of this. However, to use the root test, you need to know what the nth root of n is. Okay? So it turns out that the ratio test is the one that you try. So let's try the ratio test. So we know what an is. It's 2 to the nth over n squared. I know that an plus 1, I just put in n plus 1 for n now, right? Is going to be n plus 1 squared. Okay. So when I'm doing the ratio test, I'm looking at the limit as n goes to infinity of a sub n plus 1 over a sub n, which is 2 n plus 1 over 2n times n over n plus 1 squared. And there is a limit in there, by the way. Here, let me write that out. That looks crappy. And I'm doing a little bit, notice I'm doing a little simplifying as I'm going along. I'm taking the ratio of the squares and I'm making it the square of the ratio, right? These are things that you would do on your own if you had a little more time, right? So I know that this is n squared over n plus 1 squared. Okay. And when I simplify this, I'm going to realize that I get the limit as n goes to infinity. There's a 2 here. This just becomes 2, right? And this becomes n squared. And when I'm looking at this asymptotically, the leading term is n, right? That also becomes n squared. Everybody with me in how I went from here to here? Questions that we have? Everybody's good?
Wait, how'd you do that?
Okay, so this first term is just 2, right?
Yeah.
Okay. This term here, again, I'm looking at leading terms, okay? So there's no leading, it's just n squared. The leading term here is n, right?
Yeah.
So I just keep that. Okay.
Oh, okay.
And now I'm done. Because the limit as n goes to infinity of 2, even I can do that. That's 2, which is greater than 1, which implies by the ratio test this diverges. Okay? Everybody good on that?
Yep.
Okay, excellent. Okay, so if you tried the root test, it's a little tricky. There's one thing you need to know, and this is a really cool fact. Actually, it's a super generalization of something we talked about a second ago. So we just said a second ago that the limit of n goes to infinity of the nth root of a was 1. Turns out it's also true for n. The limit as n goes to infinity of the nth root of n is also equal to 1. Okay? And you can prove that. So notice that do you want to do L'Hopital's rule really quick and just to convince yourself? Yeah, you do. I know you do. Okay, so let's look at L'Hopital's rule. Right. So this is going to be. So if I look at this, this is n to the 1 over n power, right? So I'm going to take the log because this is infinity to the 0 power, right? So this is 1 over n natural log of n, right? And L'Hopital's rule says that I can write this now as so natural log of n over n. This is infinity over infinity. I can use L'Hopital's rule, right? Everybody's with me? I just took the natural log here, right? The natural log brings exponents down, and it multiplies it by the natural log of the base. And I'm going to realize here that I can write this just as natural log of n over n, which is infinity over infinity, so I can use L'Hopital's rule. So L'Hopital's rule says this is 1 over n divided by 1. The limit of this as n goes to 0, I'm sorry, as n goes to infinity is 0, right? So my original limit becomes 0, this just becomes e to the 0, okay, which is 1. So that's L'Hopital's. So that convinces you that this isn't a figment of my crazed imagination, all right? If you use that fact, you can use the root test. I'll show you very quickly. So remember, this was our original series, right? It went from n equal to, what was it, 3 to infinity, 2 to the nth over n squared. Okay, so with the root test, this becomes the limit as n goes to infinity to the nth root of 2n over n squared, which is the limit as n goes to infinity to the nth root of 2 to the n divided by the nth root of n squared. All right. And I can use the fact that I know first of all this is 2. Okay. So I know the limit as n goes to infinity here is just going to be 2. And I know that this limit right here is going to be the nth root of n squared, which is also going to be 2. Okay. So this number is greater than 1, therefore it diverges, which is exactly what we found out there. Okay, greater than 1. So by the root test, it diverges. However, to use the root test, and you might want to go back and think about the algebra behind this, okay? But basically, you have to use this fact here, which is not obvious, again, to most Calculus 1 students. It was not obvious to me when I was a student at all. I don't think I actually knew that as a fact. I could prove that with L'Hopital's, but I did not know that as a fact. But now you guys do. Okay. Now, this points out a really good issue, which is the fact that very often when you're doing this, there's more than one way of doing this problem. If I was a student and I was doing this initially, I might try the root test because I see that there's an exponential function. And what I'm going to find out is that it's not easy. I might get to the point where I have to evaluate the nth root of n, and I might say, you know what, I don't feel comfortable with that. So, okay, let me go ahead and try the ratio test. And the ratio test is easier. So just like with methods of integration, there's more than one way to do the method of integration sometimes. The same thing is true for testing for convergence. Which one do you use? Well, you know us, we're lazy. We use the easiest one, right? Okay. Questions on that? Everyone's good? Okay, Luke, I'll see you later. Sorry, I missed your message from before. Thanks. Okay. Last one. Then are we ready? Last one. Okay. So the last one is n squared. So this is G. We want to test the convergence from n equal 1 to infinity of n squared log n over 2 to the n. Okay. I want you to think for a second how we should proceed. Let's think about some sort of method here. Which method should we try? Which method for our test? Let me ask you a question. What is it that's making this problem hard, actually?
The natural log.
The natural log. Notice that the root and the ratio test, they play really nice with powers, exponential functions, and factorials. They do not play nice with natural logs. So natural log is being a problem. Can I get rid of the natural log somehow? So here's the thing. Unlike integration, I can replace this by another series. If I could find another series that bounded this from above and converged, I'd solve my problem. So in other words, what I'd like to find is I'd like to find another series such that the series that I'm looking at, its terms are always less than or equal to the terms for this new series, and this guy converges. This is what I'd like to find. I'd like to find another series where I could prove it converges and its terms bound my terms from above. Why? Because if I could find that, I could use the comparison test, right, to automatically say that my series converges. Does that make sense, by the way? See, if I could bound this series from above by another series, and I could prove that this series converges. If this is true, by the way, this is true for the infinite series. Everybody agrees? If it's true for every n, then it's true when I sum up all of the n's, right? Okay? And if this guy converges, it's bounded above, right? This guy has to converge. My original series therefore has to converge because I have a sequence of partial sums that's increasing and bounded above. And we said before that that's the basis for the comparison test. When you have a series whose partial sums are bounded above and the sequence itself is increasing, the sequence has to converge. So that's what I'm going to do. Questions? Okay. What can I replace this series by? So here's where I want to use a little bit about asymptotic growth. Okay. I want to replace the natural log by something, and I want to know something about the asymptotic growth, right? So here's what I'm going to use. Okay. Here's the solution. And this takes a little while to puzzle through, okay? The solution is that I know the natural log of n is less than n. This is not a statement about asymptotic growth. This is an algebraic inequality, right? This is true for all n. So I can replace natural log of n by n. Okay? So let me just be super explicit here, okay? So this is my an, n squared by natural log of n over 2 to the nth. And I'm going to replace this by a new sequence. Bn is equal to n squared times n over 2 to the nth, which is n cubed over 2 to the nth. And the reason why I'm doing that, because of this fact, I know that the ANs are always less than the BNs, right? N squared natural log of n over 2 to the nth is less than n cubed divided by 2 to the n. Does everyone agree? Okay. Now what I'm going to do is I'm going to test this infinite series. I'm going to test it for convergence. And what I'm going to find out, I'm going to do exactly what I did a second ago. I'm going to use the ratio test. And I'm going to leave this as an exercise for you to show that when you use the ratio test, the limit as n go to infinity of an plus 1 over an is 1/2, which is less than 1. Therefore, this series converges. Okay? Not the series I started off with, okay? However, because this series converges, okay, and it bounds this by the comparison test, my original series has to converge. So let me just outline this, okay? So n squared ln n of ln n over 2 to the nth is less than n cubed over 2 to the nth. That's the first fact. The second fact is that when I make an infinite series using the terms from this new sequence, I find that this converges. Okay? So it follows by the comparison test that my original series converges. Okay, it follows original series converges. Okay, so therefore I can conclude that n equal 1 to infinity, n squared natural log of n over 2 to the nth converges. Okay. This is why the comparison test is so nice. Okay, the comparison test, especially when you have natural logs, the comparison test is really nice because it lets you replace a natural log by any power of n, and you can evaluate that new series more easily. Okay. All right, that's the first 7 problems. That's all I'll do for today. I'll stop today. Any questions on anything so far?
No, sir.